generalized linear models with examples in R. And we are on question 3.22, so we're in chapter 3, question 3.22. Okay, so here's the question, and we'll just kind of, we won't read it all right here. We'll just kind of come to each question as in turn. But basically, we're looking at a data set that's called setting. And what setting is it's data about how much heat is developed while cement is setting, and the variables here, the predictor variables, are what that cement is made of, the chemicals that cement is made of here. Okay, so so let's start here. So we need to load the GLM's data package and then get our hands on the setting data. Okay, and I also want to know a little bit about the data set, so I'm going to use question mark setting. Okay, so so here we have the data sheet. So we see that A is the percentage of by weight of tricalcium aluminate, and B is some other, percentage by weight of some other substance. C, D, same thing. And then heat is the amount of heat that is evolved, well, from the cement that is comprised of these different, different ratios of these different cements. Okay. Okay. So so there we have our data. So the first thing we want to do is to plot each explanatory variable against heat evolved, and decide which constituents appear to be important. All right. So so I'm just going to plot heat against each of these variables here, and this is what we get. And so if we want to decide, well, according to the problem, which ones appear to be important, well then we would probably say B and D here, right? Because they at least have a non-infinite slope. Okay. Whereas A and C, as you vary from 0 to 20, it just seems that the amount of heat is just vertically stacked here. Okay, so it doesn't seem that A and C are having much contribution. Okay, now that is what it appears to be. Now there's a problem if we were to naively look at this and then say, well, then clearly our model needs to be heat being regressed on B and D. Okay, and we're going to look for well, we're going to see how that's a problem here in a second, but just roughly speaking, the reason that this is a problem is, so just imagine what might be happening to the chemistry of this cement, right? The amount of heat that's being generated that seems to be coming from B, well, the effect of B might actually very much depend on how much of A is in the mix, okay? And this is what regression is trying to do. It's trying to find how much independent information is contained in each variable after controlling for all of the other variables here. Okay, and we just simply cannot pick that up in these plots, right? Because whereas regression has, has access to each variable, and it's trying to figure out how much weight to assign to each variable, these plots only have access to two variables, heat and B, or heat and A, right? And so they can't account for everything else that's, possibly going on in the chemistry here. Okay, so in part 2, we're going to fit a linear regression model with A, B, C, and D, and we're not using interactions. Okay, and we're just going to look at the t-tests and compare that to what seemed to be important in the plots above. So we run this model, and we notice here that that the model is pretty ambiguous about. Well, the model is not really sure that anything is that important. Maybe A might be important, but the other predictor variables don't seem very important here. Okay, and again, why? Well, why is that in contrast to what happened with the plots? Well, like we said, these plots only have access to two variables at a time, heat and whatever the the x-axis value is. Whereas regression has access to all of them. And what regression is trying to do is to determine how much information is being imparted by each variable after controlling for the amount of information in the other variables. So, so this kind of underlines the idea that we should not look at these plots to determine what an appropriate model is. Okay. So now in part 3, we're supposed to show that there may be a problem with collinearity. Okay, and explain why this might be the case. Okay, so first of all, what is collinearity? Collinearity is where different variables or sets of variables impart this, similar information, a lot of the same information. All right, and so because different variables are contributing much of the same information, then the regression model has a very difficult time assigning how much information, unique information, came from each variable. Okay, so one way that you can kind of get your head around that is to try to solve an equation like 7 equals a plus b. Now solve for a and b. Well, you can't do that. I mean, you can. There's actually infinite solutions here, but the problem in trying to solve this is that you can pick any value for a, because there's then a corresponding value for b that will make that expression equal 7. So in other words, because there's a lot of values for a and for b that will work here, you are very uncertain about the values for a and b. And similarly, for regression, if say b and c are imparting a lot of the same information to the regression, well then the model has a very difficult time ascribing how much information should be attributed to either variable. Okay. Now how might we start to detect that collinearity is a problem? Well, actually the first way, and which I didn't write down here, but we might have picked up on something in these plots here, that collinearity might be a problem. I'm not saying that this absolutely determines that it is, but the two variables that seem to be important were kind of almost look like mirror images of one another, right? They definitely have opposite slopes, but the magnitude of those slopes seems to be similar. So it suggests that there might be some kind of collinearity taking place. I mean, but that's evidence, but weak evidence for collinearity. The next piece of information that would start to lead us here is to look at the size of these standard errors, in other words, the uncertainty, compared to the estimate values. The uncertainty is, in most cases, except for A here, larger than, in magnitude, is larger than the estimates, okay? So in other words, there's a lot of uncertainty about these estimates, and we just discussed where high uncertainty can come from, right? It can come from multicollinearity by the simple algebra problem we were trying to solve there, okay? So we can start to drill down a little bit more, looking for more evidence. So we can just look for the correlation among predictor variables here. I mean, this would be one way to start to get at it. Okay? Certainly not the best way. We'll come to the best way here in a minute. And if we look at the plot here, we notice that there's a strong negative relationship here and here, which is between variables b and d, which bears out what we saw here. All right. Well, okay, so all of that's fine and good, and that's all evidence, that's all consistent with there being a problem with multicollinearity, but really the best way to detect multicollinearity is to assess what's called the variance inflation factor, or VIF. Okay, so let's talk a little bit about VIF. What is VIF? VIF measures how much variance of a regression coefficient is increased due to multicollinearity. Okay, so now here's the formula. So if I want to know the VIF for the predictor variable xj, okay, or more precisely the coefficient of xj, but that's fine, then I apply this formula, 1 over 1 minus the r squared value sub j. Well, what is r squared sub j? R squared sub j is the r squared value from a regression where I regress the predictor variable y on everything except for xj. Okay, so let's get some intuition behind that there. So what is r squared, right? R squared is the amount of quote unquote explained variance, right? The amount of variance in the outcome variable that is explained by the predictor variables. Okay, and so 1 minus r squared would be the amount of variance not explained by the predictor variables. Okay, so now 1 minus r squared sub j, okay, this would be the amount of variance that is left unexplained after regressing on all predictor variables except for the variable xj. So imagine a scenario where xj is actually important, right? It contributes a lot of independent information that will be reflected in the fact that it will also explain a lot of the variance in the outcome variable. Okay? So if xj is informative, if I regress without xj, well then this r squared value, right, is going to be small, and 1 minus a small value is going to be pretty close to 1. And so now if I divide 1 by a value pretty close to 1, I'm going to get, you know, a reasonably small number. Okay? And that would indicate, okay, so that would mean that the variance inflation factor for xj is small. And if the variance inflation factor is small, then for a given coefficient, then it means again that that predictor variable contains information that is not contained in the other variables. Okay. Now, I don't want to start mixing up my words, and so I'm not going to go through that explanation again. But it would be the opposite scenario then if xj was not important. In other words, was not uniquely informative. Okay. In that case, you'll get a high VIF value, right? Which means that variable xj is not very informative. Okay, so try to wrap your head around that. Try to read this part right here, and hopefully you gain some intuition for that. So now we can assess VIF directly, and in R, I mean, we could just code this if we wanted to, but there's a convenient function, and it's in the car package. So we need to install and load the car package, and that command is just called VIF. Okay, and so I'm just putting in a nice little data frame here, so it's easy to look at. Okay, let that run. Okay, so here are our VIF factors, our variance inflation factors for A, B, C, and D. Okay, now in reality, each of these is pretty high. Once we get above 5, we're beginning to get a little bit concerned about multicollinearity, and they're all above 5 here. But sure enough, B and D have the highest values, and these are the ones, these are the predictor variables that seem to be most highly correlated, etc. So, so now we're also asked in this question to propose a solution to this problem. Okay. Well, the solution is we could omit B or D in regression. Okay. And again, why? Well, it's because, again, these predictor variables are containing a lot of the same information, and this is screwing up our ability to make inference. So, so we drop one of them, right, because it's duplicating a lot of information. So we drop one of them, and then run the regressions again. So here I'm dropping D, and here I'm dropping, I think, B. Okay, so we can run these. Okay, so first we'll look at A, B, C being included. Okay, so we can look here. Notice that all of the standard errors have shrunk considerably. Okay, so the model is more certain about the contributions of A, B, and C, the information that they contain. Okay. And now we actually have some significant values here. I don't know how much weight to put into significance values. This is just reflecting the more certain estimates here. Okay. And if we look at the variance inflation factors, we see that they're now all, sub 5, and so we're starting to feel reasonably good here. That this model is, adequate. So we could do the same thing by omitting B. So we omit B, run that, and we see that the standard errors have reduced substantially, okay? And the variance inflation factors have reduced substantially. Okay. So I think that is it for this one.